Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video, Inverse Trigonometric Functions, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the video, Trigonometry in the Unit Circle, before watching this video. In this video, we will be reviewing inverse functions, discussing inverse trigonometric functions, and solving equations that contain inverse trigonometric terms. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs of a function, then f is one-to-one if f of x1 is not equal to f of x2. Suppose that f is a one-to-one function. Then, corresponding to each x in the domain of f, there is exactly one y in the range, because f is a function. And corresponding to each y in the range of f, there is exactly one x in the domain, because f is one-to-one. The correspondence from the range of f back to the domain of f is called the inverse function of f. The symbol f with a -1 superscript is used to denote the inverse function of f. Find the inverse of the following function. F of x is equal to 3x plus 4. It will be helpful to establish the domain and range of this function, both of which are all real numbers. First, we have to determine if it has an inverse. We do this by graphing the function. Previously, we applied the vertical line test to determine that a relation is actually a function. Here we use the horizontal line test. Similar to the vertical test, if the horizontal line intersects the graph of the function at only one point, then the function is also one-to-one and thus has an inverse. Now that we have determined that the relation is both a function and one-to-one, we can find the inverse. We do this by expressing the function as y equals 3x plus 4. We then swap x and y, giving us x equals 3y plus 4, then solve for y. Subtract 4 from both sides, then divide by 3 to get y equals x minus 4 over 3. This means the inverse function of f is x minus 4 over 3. This is the graph of the inverse function. Note that this graph is symmetric with the original function about the line y equals x. Another method of verifying that a function is the inverse of another function is to take the composite. If the two functions are inverses of each other, then f inverse of f of x will equal x, and f of f inverse of x will also result in x. Next, let's look at some other functions and their inverses you should be familiar with. For example, f of x is equal to e to the x. The domain of this function is all real numbers, and the range is all numbers greater than 0. This is the graph of the function. This function passes the horizontal line test, so it is one-to-one. To find the inverse, set y equal to e to the x, then swap x and y and solve for y. Take the natural log to cancel e. Therefore, the inverse of e to the x is the natural log of x. The domain of this function is all x is greater than 0, and the range is all real numbers. This is the graph of the natural log of x compared to e to the x. Notice that the two graphs mirror each other across the line y equals x. The next function we'll study is g of x is equal to 1 over x. The domain of this function is all x is not equal to 0, and the range is all y is not equal to 0. This is the graph of the function, and note that it passes the horizontal line test, and as such is one-to-one. Set y equal to 1 over x, then swap x and y and solve for y, giving us the inverse function 1 over x. This function is symmetric across the line y equals x and has the same domain and range as the original function. Finally, let's look at h of x is equal to x squared. The domain of this function is all real numbers, and the range is all numbers greater than or equal to 0. Note the graph of the function. This function, though, fails the horizontal line test and is therefore not one-to-one. In this case, though, we can constrain the domain of the function to be x is greater than or equal to 0. Under this constraint, the function passes the horizontal line test and is one-to-one. We then find the inverse. Y equals x squared, then x equals y squared. Take the square root of both sides to get the inverse function y is equal to the square root of x. The domain of this function is all x is greater than or equal to 0, and the range is all y is greater than or equal to 0. Compare the graphs, and you'll see that they are symmetric across the line y equals x. Let's now explore how the trigonometric functions work with an inverse. For example, let's evaluate f of x is equal to sine x. The domain of the function is all real numbers, and the range is from -1 to +1. This is the graph of the function. We can clearly see that this function fails the horizontal line test and as such is not one-to-one. But just as before, if we constrain the domain, in this case to between -π/2 to π/2, then the function passes the horizontal line test and is one-to-one. Next, we express the function as y equals sine x, then swap the variables to get x equals sine y. Solving for y, we get y equals inverse sine of x. This may also be called the arcsine of x. Therefore, the inverse function of sine x is arcsine x. The domain of this function is from -1 to +1, and the range is from -π/2 to π/2. In summary, the arcsine of sine x equals x, where x is between -π/2 and π/2, and sine of arcsine of x is equal to x, where x is between -1 and +1. Next, let's review each trigonometric function and their inverses. Y equals arcsine of x means x is equal to sine y for x between -1 and +1, and y between -π/2 and +π/2. Y is equal to arc cosecant x means x is equal to cosecant y for the absolute value of x greater than or equal to 1, and y between -π/2 and +π/2, and y is not equal to 0. Y equals arc cosine of x means x equals cosine y for x between -1 and +1, and y is between 0 and pi. Y is equal to arc secant x means x is equal to secant y for the absolute value of x greater than or equal to 1, and y between 0 and pi, and y not equal to π/2. Y equals arc tangent of x means x equals tangent y for all real numbers x, and y between -π/2 and +π/2. Y is equal to arc cotangent x means x is equal to cotangent y for all real numbers x, and y between 0 and pi. As an example, let's find the arcsine of -1. For this, we will use the unit circle. First, we note that the range of arcsine is limited to -π/2 to π/2. Then, we look for an angle theta, where sine theta equals -1. This angle is 3π/2, or expressed in our range, -π/2. Next, let's find the solution to arc cosine of 1/2. The range of arc cosine is 0 to pi. We then look for an angle theta whose cosine theta equals 1/2. This angle is pi/3. Finally, arctangent -1. The range of arctangent is from -π/2 to pi/2. So we look for an angle where sine and cosine is the same solution, except one is negative and the other positive. This occurs at 7π/4, or -π/4, within the range of arctangent. In these examples, we will solve a compound expression. First, arc cosine of cosine 2π/3. First, we solve the expression inside the parentheses. Referencing the unit circle, cosine 2π/3 is -1/2. Arc cosine of -1/2 is then 2π/3. Since the solution occurs in the range of arc cosine, which is 0 to pi, then the solution acts as an inverse function. Next, let's look at the arcsine of sine 11π/4. For 11π/4, we use the equality sine theta equals sine 2k pi plus theta. If k equals 1, then 11π/4 minus 2 pi, or 8π/4 with a common denominator, equals 3π/4. Therefore, sine 11π/4 equals sine 3π/4. Referring to the unit circle, sine 3π/4 equals the square root of 2/2. The arcsine of the square root of 2 over 2, using the range from negative pi over 2 to pi over 2, is pi over 4. Finally, let's find the arctangent of tangent negative 2 pi over 3. From the unit circle, tangent negative 2 pi over 3 equals the square root of 3. Since arctangent has a range from negative pi over 2 to pi over 2, we find an angle theta where tangent theta equals the same square root of 3. This happens at pi over 3. As another example, find the sine of arc cosine 1/2. Looking at the unit circle, arc cosine of 1/2 on the interval 0 to pi is pi over 3. Sine pi over 3 equals the square root of 3 over 2. Next, let's find tangent of arcsine 1 over 3. In this problem, there is no 1 over 3 referenced on the unit circle, so we will not use it. For this expression, we first evaluate arcsine of 1 over 3. This implies there is an angle theta that satisfies sine theta equals 1 over 3. For this, we use the right triangle and establish an angle theta. The expression then means the opposite side equals 1 and the hypotenuse equals 3. We use the Pythagorean theorem to find the adjacent side. 1 squared plus b squared equals 3 squared. B squared equals 8. B equals 2 times the square root of 2. Therefore, if sine theta equals 1 over 3, tangent theta equals 1 over 2 times the square root of 2. We rationalize the denominator to get our final answer, the square root of 2 over 4. Equations involving trigonometric functions can now be solved using the techniques previously discussed in this video. In many of these equations, a defined interval will be required to limit the number of possible answers. For example, solve the following equations for theta on the interval 0 to 2 pi. First, 2 sine theta plus 3 equals 2. First, we subtract 3 from both sides to get 2 sine theta equals negative 1. Then divide by 2. Sine theta equals negative 1/2, or theta equals arcsine of negative 1/2. Referencing the unit circle, we find that theta equals 7 pi over 6 and 11 pi over 6. Next, solve 2 cosine squared theta plus cosine theta minus 1 equals 0. This equation has 3 terms, with the first one being a square, the second having the same function but not squared, and a third term being an integer, all equal to 0. This is a form of a quadratic equation. The left side can then be factored into 2 cosine theta minus 1 and cosine theta plus 1. The product of these equals 0. Therefore, either 2 cosine theta minus 1 equals 0, or cosine theta plus 1 equals 0. On the first equation, add 1 to both sides and divide by 2 to get cosine theta equals 1/2, or theta equals the arc cosine of 1/2. Referencing the unit circle, we find 2 answers on the given interval, pi over 3 and 5 pi over 3. Next, the second equation, subtract 1 from both sides to get cosine theta equals negative 1, where theta equals arc cosine of negative 1. From the unit circle again, the only solution this time is pi. Therefore, the solution set includes pi over 3, pi, and 5 pi over 3. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.